Welcome to Zero Knowledge, a podcast where we talk about the latest in zero-knowledge research and the decentralized web. The show is hosted by me, Anna.
And me, Frederick.
This week, we catch up with Howard Wu and learn about his new project, Aleo, which is built around the ZEXE ZK construction. But before we start in, I want to say thank you to this week's sponsor, Least Authority. Least Authority is a security consulting company known for their dedication to privacy-respecting solutions and boundary-pushing technology. They are a team of security researchers, open-source developers, privacy advocates, and cryptographers specialized in security audits, design specification reviews, and security by design. You may know them as the team behind the security audits and reviews of the ETH 2.0 specification, Protocol Labs' Gossipsub protocol, Zcash's Sapling upgrade, Tezos Foundation's TzBTC, Blockstack's investor wallet, MetaMask's Lavamoat, and more. Beyond auditing, they also have extensive experience in building distributed systems, helping to improve privacy-enhancing tools, and making regular contributions to open-source software projects. If you are looking to improve the security of your protocol or verify your use of cryptography, including zero-knowledge proofs anytime from design to implementation, you can schedule a no-obligation call to find out how Least Authority can help on your project. Visit their website, leastauthority.com, and hit the Schedule a Call button to book one of these calls. I've added the link in the show notes. So thank you again, Least Authority. And now here's our interview with Howard. We have today on the call Howard. How you doing, Howard?
I'm good, and thank you for having me on.
So Howard has already been on the show. We actually did this episode on ZK SNARKs. It was one of the most popular episodes I think we've had on the Zero Knowledge podcast. And in that, we actually did introduce Howard quite extensively. And so you might want to listen to that episode. I'll add the link in the show notes. But just briefly, Howard is a researcher at Berkeley. He co-founded the Decrypt Capital VC and is also the co-founder of a new enterprise called Aleo. And actually, just as a side note, I've actually been freelancing with Aleo. I've been working on a very specific thing, and I don't know that much about all of the other parts of Aleo. So this is a chance for me to also explore this project a little bit deeper.
I'm pretty excited to talk about this, and I'm also really glad that we're finally public. It's been about a year of work that we've been working on in stealth, and in the past 48 hours since coming public, I've been getting a number of emails and also messages from people. There's now a developer preview that we've put online, and people have started filing bugs and also joining our Discord to give us messages there. And it's just been a very exciting time.
Cool. Maybe to set the background a little bit, I know very little about this project other than the public announcement. What was the spawn of this? Why did you start working on this? Like, what was it that made you go? Like, what was the problem, or what was the inspiration that made you kick this off?
Okay, sure. Yeah, so I guess like over the past year, I've been thinking about ways for applications to become more personal and more private. Today, the model on the web is very much about providing free services in exchange for personal data. And, one of the things that I really want is just to be able to use my apps in peace. I want to be able to use personal apps without needing to hand over my personal data. And I want applications that can also let me decide when and how my data is being used and actually enforce that. And so, in building Aleo, my goal has really been to build web services that can become truly personal, living in places more than just your browser, and also provide an experience that is really tailored for you, where you still have control over your information.
In the previous episode we had you on, I think we would have done your background from, start to then. And so anyone who's curious about maybe that background, I'll put a link in the show notes to that episode if you hadn't heard it already. But I'd be curious to hear a little bit, like, since then, you were working in academia and you were working in VC. And I'm curious, like, what did you learn in that time that sort of made this idea pop into your mind?
I think the number of experiences that I've had over the past few years have taught me a lot of things. Like, first, I've seen a lot of projects within crypto build out ecosystems and communities, and I've also seen a number of applications enabled on blockchains. One of the things that I've wanted over the past few years is this ability to have private and programmable applications, which hasn't been possible thus far. And that was also why, we worked on ZEXE. We looked at the ecosystem and realized, there's kind of two axes you can really evaluate crypto on, and one is on programmability and the other is on privacy. And, Bitcoin is rather low on both. Ethereum goes one direction to offer high programmability, and Zcash goes the other direction to offer high privacy. But there's this upper right-hand quadrant of high programmability and high privacy that's really missing. And, it's an area that we said, why don't we take a stab at it? I've wanted to see applications like this, for many years now. And that was how ZEXE was born. We ended up publishing that as a paper about it. It just debuted this year. And we published the code last year, for people to start trying and using it. Since then the reception has been quite strong and positive. People have been really interested in, applications like using decentralized dark pools or mixers for it. This is an area that I think, Ethereum has a lot going for it, but it doesn't have the foundation to actually support these types of applications. And it's something that for me, I've wanted to see out there, and it's something that we've been then tinkering with and trying to make possible.
Did you ever try, when you were doing more of the VC stuff, did you ever kind of try to find a team to do it? Were you ever like, hey, there's this great technology that we came up with, a system that we came up with. Do you want to build it? Or were you always in the back of your mind thinking this is mine?
I definitely did not plan on doing this. Certainly my role as a VC, we tried finding teams to commercialize ZEXE. And one of the challenges that we found was just finding good pairs of people is really hard for this particular problem. You have a very complex technology with a market where people not only have to understand the technology, but they have to be able to explain it well to other people. And combining, the business and the development side, we found was really difficult. And after, a year or so of this, Matt and Ian were the ones who actually really were asking me about commercializing it myself. And, after much thought and discussion, I said, why don't we see if we can assemble a team? And somewhere around middle of last year, towards the end of the year, we realized that we could, and we said, why don't we give it a shot? And, that was how Aleo was born.
Cool.
So, like Anna mentioned earlier, we had an episode with Pratush about ZEXE in particular, and we'll link that. I'm curious, in part, also what your involvement on ZEXE has been, but also, again, do a recap of what ZEXE is. As you mentioned, it's in this cross between private and programmable, but how does it actually achieve that?
Yeah, so at its core, ZEXE, which stands for Zero Knowledge Executions, is a decentralized private computation protocol. The idea is that we're using zero knowledge proofs to enable private applications in a recursive manner. The high level of ZEXE is that there's really two things that we really wanted to achieve with it. The first one was to offer full privacy for applications. And what we mean by that is that we delineate in the paper two levels of privacy. One is data privacy, and the second is functional privacy. And data privacy is quite intuitive. The idea is that if you and I are communicating or you and I are interacting, only you and I should see this information. And what functional privacy means here is that in addition to just our data being private, the application that we're using here also is not known to the public. So from an Ethereum perspective, you could think about it like, not only do we not know the amounts within an ERC20 transfer, we don't even know the fact that you are using this specific ERC20 token or even an ERC20 contract at all. Mm-hmm. And so that's the conceptual idea on privacy here. And the second is really around providing a more scalable solution. And by scalable, people like to talk about TPS. From our perspective, we've been looking at scalability in terms of the size of applications. So on Ethereum, because there is roughly 10-second blocks and you have a block gas limit that you have to abide by, applications can only run for so long. And so the way that we get around this is effectively performing those types of application runtimes off-chain and merely verifying the proofs on-chain. And so by doing that, you can, as a miner, just check the output along with the proof and know for a fact that this state transition is correct. And by doing it this way, it's far more scalable because it allows the miners to spend less time checking every execution, but also that every execution can be, the same amount of time to check. And because of that, that you can fit far more transactions into a block. And this is also a way for applications to run for much longer than that little time slice that they're actually being given.
You just mentioned this recursive feature of the ZEXE protocol. I don't know if it's easy to do this, but I was kind of trying to picture how that compared to something that we are more familiar with, like the Zcash transaction, where there's a snark prepared for each transaction. When you say recursive, is it each transaction then does a snark of the entire blockchain rather than it just being a snark attached to a transaction?
Yeah. So when I mean recursion, actually, there's different types. So in terms of recursion, the approach that we took in ZEXE was to have a recursion of depth 2. And so it was a fixed step recursion.
Okay.
There's also, a lineage of recursion that is more common, which is to have cycles of pairing friendly elliptic curves be used. And by doing it this way, you can kind of have quote unquote infinite recursion. In our case, the motivation for having this recursion is specifically for privacy, for every transaction. So instead of having transactions themselves publish proofs about the runtime, we are actually verifying the proofs about those application runtimes and then bundling those into a transaction proof in order for that to be published and so that the application data itself isn't visible. This approach lets us achieve that level of functional privacy because the application proofs themselves are actually checked within an outer proof.
But is that recursion? You say it's only level 2. It's is that how you described it? I've heard that said a few different ways, recurse.
Depth 2.
Depth
recursion?
2, yeah. Layer 2. Okay, anyway.
Yeah.
But I guess, are you doing that for compression in any way? Is it to make it smaller as well? Are you combining lots of them under one of these recursive snarks and then making it smaller?
Yeah, that's definitely another added benefit is that by checking multiple proofs here within one single invocation, you actually compress the transaction so that you can bundle, in our case, in the example in ZEXE is 2 and 2 out, that you can actually compress those 4 proofs into just one proof. And because of that, you actually save space, as an added benefit.
Mm.
But the main purpose is functional privacy, right? It's not you're not doing it because of compression.
Yeah, it comes as a side effect for free, and it's certainly nicer to be more efficient also in space.
Yeah. And I would encourage anyone who really wants to dig in deep on how ZEXE works to just listen to the episode with Pratush where he explains the birth scripts and death scripts and how all this works. Something that we touched on in that episode, though, is the ergonomics of programming in ZEXE, which is a huge problem, or it's something that we discussed back then, and the problem being that you need a trusted setup for each new type of application. The programming model is very different from Ethereum, so you need to rejigger how you think about smart contracts. It's not one contract that just lives in a place, but created and destroyed when you move coins around or move UTXOs around. I mean, I suppose this is, to some degree, what you try to address when you build a product around it. But before we get too deep into the company, the product side of it, maybe what are your thoughts on those? Are these problems that are fundamental or can they be solved?
Yeah, so in terms of the developer experience for writing applications in this ZEXE model, it's something that I think can certainly be improved upon. The way that we architected ZEXE was to allow for any type of NISC here to be used for applications. And, this could be anything from Grot16 SNARKs up to universal SNARKs. But also you can use, bulletproofs or Starks. And this model is meant to be general for different types of primitives. In our case, the proof system that we are actually using for Aleo is Marlin. And the rationale for that was to design a system for applications where developers don't have to run a trusted setup for every app. It would be a huge barrier to entry, in my opinion, and it would also just be a huge pain for developers to have to reason about. And so from our perspective, it was something that we thought was very important, and it's updatable, which is a really nice property to have here. In terms of the actual programming model, it's something that in the paper we provided 3 examples for. So the first one was, private custom assets. The second was private stable coins, which are things that allow you to attach policies to them. And then the third was a private DEX. And we gave 2 different variants in the paper for that. These are applications that we think, in crypto are already kind of widely adopted or widely accepted, and we wanted to show what the privacy-preserving variant of those could be. Even since then, we've been evolving the original designs of that in the paper so that it's more encompassing, it's more secure, it's also more performant, and that's an area that we think is also very exciting.
So I think at this stage, we've refreshed a little bit the story of ZEXE and the story of how it works and some of the challenges. And now you've started to explain, how these challenges have been taken on, but we should actually describe Aleo and actually introduce Aleo maybe a little bit more now. So what is Aleo? What is this company? What is it doing?
So the idea for Aleo is to build a platform that is fully private and to support applications that can be both truly personal and truly private. Over the past few years, one of the things that I've grown to care deeply about is this ability to own your data and for information to be, private. I think one of the really cool things that zero knowledge proofs enables is this ability for you to run your computations on private information without revealing it to other parties. And as part of that, I've been exploring these ideas, especially with respect to the web, on how you can provide user experiences that are truly private for the end user, while providing the service providers themselves with the correct information, the correct state to continue serving them correctly. And this is a model that I think is really underexplored, especially in the context of the web today. The web itself has a model that requires users to kind of exchange their personal data for free services, and I think that this model not only is antiquated, but it's also really incentive incompatible for the user and for the provider. I think that there are far more clever models that people are starting to realize and also reason about, and for me, it's something that I find very interesting and fascinating to explore.
What was your experience at Decrypt? You worked in academia and VC, so you had access to so many different projects. But in that process, something dawned on you that made you feel like you needed to build this company. What was that? What was the spark that really made you go, no, there's something still missing?
One of my frustrations with the blockchain industry as a whole is just this general trend towards building solutions in search of problems. I personally think that it's important to work backwards by starting at the user experience and trying to find the technologies you need to actually go build those solutions. I think we have a real shot at positioning Aleo to address a lot of the shortcomings in crypto. For one, I think deeply about user problems in general. It's something that I spend a lot of time on every day. And one of the areas that I really wanted to hit with Aleo was just solving for the web. The web is a phenomenal place. It's a place that really connects us and allows us, especially during a time of COVID, to actually stay in touch with each other. But at the same time, we know that freedom on the web is going down, that censorship is going up, and just the quality, the experience of the web itself is degrading. There's fake news. There's all these different advertising platforms that are taking over. There's a lot of spam that's being pushed to users, and we see it on our devices every day. It's a fundamental user experience that I think could be far better. And I think that the business model of the web itself could even be completely changed. And, I think we have a real shot at making the web a better place. And, Aleo is designed to actually provide that type of experience. And, zero knowledge itself is a phenomenal technology for enabling that. We don't have this notion of private web data today. And everything is starting to become a public commodity. If you look at your household, there's just devices everywhere now, and we become more web connected physically in our personal space than ever before. In the wrong hands, this type of technology is very clearly able to become a type of big brother experience where, it's not something that we want, or it's not something that we intended to build for. And I think that being able to separate public web data from private web data is an important thing, especially for this next decade. The internet's going to become pervasive. It's going to become incredibly personal. And I think that if we don't actually go for building the platform that allows private applications, we might not get it. And so for me, it's about building a web experience that actually addresses this shortcoming and provide with zero knowledge, a technology that actually can enable this in the right way. I think that, it's a value proposition that should be open source. It should be permissionless, and we should allow anyone to, contribute and participate towards, because it's something that affects every one of us. As we become more web connected, it will only become more apparent to people.
When you talk about this, we have critique of the web, but I guess how do you undo this model that exists? Do you still have to keep a foot in the web in order to do that?
Well, first off, I think the web is a really cool place, and it doesn't make sense to try to replace it. We've grown used to it, we've grown accustomed to it, and more so, it's become a real part of our daily lives. I think what makes sense really is to build an experience that is integrated with the web, it's cohesive with it, and it actually helps to unlock new value on the web. So the purpose here is really to provide an experience for users where, these types of services really live on the client side. And instead of having to send your data over to the server, you actually can just get transparent algorithms from the server and run it on the client side. For both sides, there's certainly benefits. From the user's perspective, they're no longer forced to give up their data in exchange for services that they want at the cost of their personal privacy. But also for the provider, they don't have to bear the risk of managing user data to provide their service. So that means that they don't have to face the implications of storing, processing, and reporting it. In this model, I think it's one that really allows the users and providers to be incentive aligned, because they're no longer in this game where reputationally, the provider is taking on all the risk for the user, and the user is forced to give up all of their information in exchange for that service.
It is obviously a common complaint, especially in the blockchain world, of the web is broken and we need to fix it. And it's always interesting to see how people argue, do we integrate, do we provide something new? I think both paths are fine, but you kind of have to keep in mind the user, right? If you're providing something new, you need to get over that inertia of the web and get someone to download a new kind of thing and get them to understand why they should do that. I think that's a massive task. While if you can integrate with the existing web and just provide some more value or some clearer, you actually own your data on this website, then I think that's a lot easier path to go as well. Because ultimately, we're only interested in solving problems for people and doing what they find valuable. So I think if you can meet them where they are, it's a lot easier. But for me, this brings up a huge question. I mean, with what you just described, we are in this world where we give data to companies for a free service. But this is spawned from the advertising industry, and it's spawned from a place where people decided at some point they don't want to pay for things anymore, right? They'd rather get it for free and give up their privacy. How do you reverse that trend and tell someone you now have to pay? Or if they don't, then what's the business model for the provider?
So in terms of, business models, I personally think that, first off, that model remains cohesive in this new architecture. But at the same time, I think what this provides is more choice for users. On the web today, there is no simple way for them to pay for things. There is no simple way for them to bill for things. And having micropayments and having the ability to actually charge from a resource perspective is quite difficult right now. And as we explore the different types of assets that now exist within crypto, I think it's starting to show that there is more forms of payments than merely just money on its own, that services and assets themselves more broadly can be used in exchange for other things. And this is almost like going to this concept around bartering, but with a model that is far more scalable now. And from this perspective, I think these types of transactions allow you to actually pay for services fairly without having to give up your data in exchange for it. But I would also emphasize and stress that, for services that want to collect your data and use your data, I have no issues with that. What I really find issue with is when they don't tell that to you upfront and transparently. I think thus far today, we don't really have good technologies to go and enforce that they're using your data responsibly. And once your data is in their hands, there's no takebacks. So it's very hard for us to control it. And because of that, we don't really have the power here. And so what this model really is trying to do is to open up the types of options or opportunities that both users and providers can explore and find the one that meets their needs. I think that when it comes to user payments, it's certainly one model where on the web today, it's virtually impossible to do that at scale for every small item that you want to receive or for every small bit of streaming that you want to do. And in this model, it's something that you actually could give people the option to have.
I wonder, the thing is, some of these topics, this idea of privacy and putting more power into the hands of people, this does come up often with the projects that we interview. And so I'm kind of wondering, how does Aleo line up when you think of projects like Aztec or Matter or Findora or Coda? These are sort of very zero knowledge focused projects. Where do you position Aleo when you compare it to them?
My personal belief is that in terms of what we're building, the technology needs to sit on a new stack. To allow for privacy for applications, you really need to build a system from the ground up that is private by default. And we see this today already on Ethereum. Without privacy, applications like smart contract mixers or dark pools can't fully protect user activity. It just doesn't work. And for companies who actually want that and want the scale associated with off-chain computations, there is no good combination for that today. That's where, we've certainly thought about building this as a solution on Ethereum. We've certainly considered other architectures as well. And at the end of the day, one of the things that continues to come back to us is the complexity and challenges of building a system like Aleo on a layer one that isn't private by default.
So I think we've defined philosophically what Aleo is and what it aims to do. But what is Aleo? What is it? What are the pieces of this project?
So Aleo is a platform that is decentralized. It has a blockchain, and it uses this blockchain to verify and store proofs. These proofs are effectively ZEXE transactions, and the architecture that we went for was something that was Bitcoin-like. So, in ZEXE, we talk about a ledger, and we adhere to what looks like a UTXO model here. And for consensus, we've been developing something that is very much Snark friendly. So, one of my personal goals, which is less about the web, is this ability to have zero knowledge proofs in kind of mainstream audiences. And one of the biggest barriers to getting there today is this ability to performantly compute zero knowledge proofs. I don't have a hardware background myself, and neither do people on our team. But what we do have is the ability to design incentives and incentive mechanisms. And what we decided was to build a consensus algorithm that adhered to the same type of cryptographic stack as the applications that would live on Aleo, and use that to basically incentivize miners to develop hardware acceleration for SNARKs. I think that the ability to have really performant SNARKs is really cool, but it's also one that we've seen even from the traditional computing industry from many decades ago. If you look at many of the cryptographic algorithms that are commonplace today, for example, for HTTPS, those types of operations under the hood are really slow in software, relatively speaking. And it wasn't until, companies like Intel started adding these cryptographic units into every CPU that's shipped, that these algorithms actually became performant. And because of that, we almost take HTTPS for granted today, but these types of technologies, required real hardware to be baked into every chip for every device in the world in order to be practical for use. And I think that we're in a very similar story here. And the hope is that we can bring verifiable computations, and the goal is to bring verifiable computations to mainstream audiences.
And this idea where the consensus, so the mining of this blockchain also, like whatever that action is under the hood, the thing that people are going to spend money buying hardware to potentially do and earn from it, that process is actually useful throughout the rest of the system.
Yeah. I guess the best way to talk about it is, so the consensus algorithm that we've been working on is called Proof-of-Succinct-Work, and it's based on Proof-of-Necessary-Work with Akis.
Who we've had on the show a few weeks ago, and I'll add the link to that as well.
So the idea for us has been, instead of going down the path of a succinct blockchain, we've been more interested in using Aleo for interoperability and also for building efficient light clients. And one of the things that we wanted to do was to have this consensus algorithm be useful work. And instead of actually checking the entire history of a blockchain, we wanted to confirm that a transaction is actually included in a block. And so in our architecture, this circuit is effectively checking a Merkle tree about transactions that are included in that block. And it's a very convenient way for, a smart contract on another system to verify that a transaction was actually included in block, 58 on Aleo by just verifying a proof. So this model is very nice for interop, but it's also great for light clients because it's a very simple way to say, if I'm downloading a block's data, I can check very quickly that these transactions really were included in a specific block without having to process them individually from Genesis again.
That's interesting. So it's proof of work where the work is generating proofs that the transactions are in the block.
Yeah. So the best way to think about it is similar to Bitcoin, it's a proof of work consensus algorithm, but instead of grinding SHA-256, we're grinding SNARKs here. And by doing that, the goal is to incentivize miners to develop hardware acceleration for SNARKs so that we can make these types of computations a commodity and commonplace. By doing that and creating that incentive, application developers on Aleo can actually run their applications, on ideally various service providers who happen to now have the choice of saying, if market demand says that, there's a lot of programs and people want to pay a lot of transaction fees to run their programs, great, I will target my hardware for those types of programs. But if suddenly there's a drop in activity, it's not that these chips are useless. There's still a blockchain here where I can actually mine new blocks on and get a block reward for, and they can then target it for that instead. I think that that's also something that will be useful for companies like Matter or for Aztec, where, they are building validators for rollups. And these rollup validators themselves are, designed to be very performant for computing zero-knowledge proofs. And in the case that there is low traffic for rollup transactions, they could also use their hardware to actually target mining blocks on Aleo. And this gives an ability for, validators there to actually have some constant or more stable type of revenue.
Mm. But is when you're saying grinding the SNARKs, when you're actually proving them or going you're using that the work is the SNARK generation, is it useful SNARKs or is it useless SNARKs? Is it just the act of proving a SNARK, or are you actually attaching that to something else?
So the circuit itself is effectively a small Merkle tree. And this Merkle tree is meant to represent, the state of this block. So by performing this type of work, well, for one, we're basically asking the miner to now check that the transactions are included in this block. But then for the rest of time, every node no longer has to perform that inclusion check themselves because they can simply verify this proof to ensure that they actually have the right block data. And this is a really nice feature to have because it saves on all future participants for the rest of history from having to do extra cycles of computations for themselves. And it saves on a lot of work then.
Is there also a proof that I'm on the correct chain? Talking about light clients.
So consensus about which chain you're on or which network you're on is a really hard problem. And it kind of gets back to just what is the source of truth. So in this case, it doesn't do that. And it's also one that's, more fundamentally just a question on consensus on what is the most common or what is the right state.
Yeah. So back to Anna's question, I guess to keep talking about light clients, normally a light client syncs the whole header chain to know that they're in the right place. And then they go, I want to know either some state or like in Bitcoin, I want to know whether this transaction is included or not. And then they go ask a full node, is this transaction included? And the full node replies, well, I'm at this block with this hash, and this is the Merkle tree here, and this is the transaction. So you can now, here's a Merkle proof that it is here. So what you're doing is, because you have this proof of work that proves the inclusion, the full node doesn't have to reply perhaps with anything. That's a question. But even if they did have to reply with anything, they just reply with the Snark proof saying, here's a proof that it is.
Yeah, it ends up being a proof of inclusion for that transaction, and it's something that is even composable. So, for example, if you really wanted to give a proof that not only was this transaction included in this block, but it was included in this block that now has 6 confirmations, what you could do is actually take 6 of those proofs in those blocks and actually then recursively come up with one new proof on top that actually checks that those 6 block proofs are indeed valid and that this transaction then was included in the most recent of that. And then you can send that over, say, to a smart contract to go and check there, just one proof instead of 6. And by doing it this way, it's far more efficient for actually doing interoperability, but it's also a really nice way for light clients to just quickly validate, if I really want this transaction and want to know that this thing really was included on this ledger at this block, they can.
I mean, a question for me immediately is, do light clients still just sync the header chain? Or, I mean, it feels like it would make sense for them to sync the header chain and all of the proofs. Like, depending on how large the proofs are, but like the difference between a light client and a full node is not necessarily that it's cheaper on data, but that you don't re-execute the transactions. But if you synced all of the proofs, then you still don't have to re-execute the transactions. You can just verify the proof.
Yeah. I mean, in this model, because the VM doesn't live on chain, there is actually never even execution for the full nodes themselves. Everyone on Aleo just has to verify proofs, and these proofs will ensure that the transactions themselves are valid state transitions.
Yeah. So you're almost collapsing the roles. Like a light client and a full node is basically the same thing. I mean, you could construct a lighter light client that doesn't have all of the data or something that is selective in what it downloads, but it's more or less the same thing.
Yeah. The idea really is to make it crypto-economically well incentivized. The idea being that on Ethereum today, for a miner, they have to reason over whether to spend their cycles checking a transaction or trying to mine the next block effectively. And it's far more efficient to say, you don't have to re-execute these transactions from Genesis forever in order to verify this block. And instead, you can just spend your cycles mining. I think that from that perspective, it's also, far more efficient, quote unquote, gas wise, because, everyone gets and only needs the same amount of time, per transaction to be reasoned on, in order for that transaction to be included in a block. In this case, we're talking constant times of, somewhere around 3 milliseconds. And because of that, no one needs any more time than that. So it's a really nice benefit to have in this architecture.
I know ZEXE, the ZEXE curve, the ZEXE concept has also been implemented in Plumo, this light client on the Celo construction. Is there any relationship to that? Is it similar?
Yeah, so the Celo folks are using the ZEXE curves. They aren't using the ZEXE transaction model. More so, the curves provide recursion, which is really useful in their case, if I understand correctly, for proof of stake in leader election, and also then composing the state of every round for their blocks. And so in that model, they are using BLS 12377, and to my knowledge, they are exploring using BW6 for then doing block compression-like techniques.
But I guess in yours, it's different because this light client could almost be this main node at the same time, like where Frederick's saying that they're kind of merging of roles. In their case, they have a more traditional blockchain where they're using this ZEXE curve for purely the light client.
Yeah, like the difference I would say is that For transactions here on Aleo, they are actual ZEXE transactions. And so because of that, every execution is private, and every execution comes with a zero knowledge proof. In the Celo model, to my understanding, it's effectively a fork of Geth, where transactions adhere to the smart contract and Ethereum model. Rather for validators, they are now, constructing signatures for the next block. And by having a proof about these signatures, it's a very easy way to make sure that since Genesis, that your block history is correct and that you're actually synced to the right block as the latest block.
Yeah, that is the point of the Celo proof is like what I said, to prove that you're on the correct chain, basically. As far as I know, they bake in some origin hash to prevent long-range attacks and basically say this is the chain that it's supposed to be. And then you have these intermittent proofs that you just sync those proofs rather than syncing the whole header chain. So it's just a faster way to sync alike lines rather than providing any privacy or any other thing. It's just faster syncing.
Yeah.
One of the things that I wanted to sort of dig into was a little bit like the different SNARKs in the system. Like the ZEXE curve itself, did it have a variety of different SNARKs in it acting at the same time?
Yeah, so in ZEXE, we have a few circuits, and these circuits are used to make attestations of validity for different statements. For example, there's the inner SNARK here, where the inner SNARK is responsible, one, with checking that a transaction is actually based on correct ledger state. So the way that a ZEXE transaction works deep down is that we have serial numbers and commitments. The commitments are generated when you create a new transaction, and the serial numbers are revealed when you spend a record. And so in this model, the commitments themselves are composed into one giant Merkle tree to represent the state of the ledger. And with the inner SNARK, we're actually taking the root of that tree, the ledger digest, and checking that when we're spending a record, that its corresponding commitment actually lies in that Merkle tree. With the outer SNARK, it does something a little bit different. So the outer SNARK is the circuit here that is actually, one, checking the inner circuit's proof, but then two, it's also checking the input, the death programs and the birth programs proofs. So for every transaction, you're reasoning over, spending some records and birthing some new records. And with each of those, it's basically an application runtime where you are composing a new proof for each of those. In this model, the outer SNARK can check, for example, 4 proofs, so 2 in, 2 out, and compress those as part of that, but also hide the application that you're running because the proofs themselves of those state transitions are no longer public here. And at the end, all you have is this outer SNARK proof, which is what you actually bundle in your transaction and publish on chain for people.
And is it that ends up in the Proof-of-Succinct-Work?
Exactly. So that's the actual...
Okay,
yeah.
That's the connection then. So this is the connection between ZEXE and the Proof-of-Succinct-Work. This has remained a complete mystery to me until now. This is awesome. Cool.
So those transactions actually form the leaf of the Merkle tree that is then passed in for the actual Proof-of-Succinct-Work to check and base itself on.
Okay. It's basically like all of these SNARKs and with different purposes happening in parallel, I guess. And then those are in a way compressed, but also made private through this outer SNARK. And I know you just said it, but I can't remember exactly how you just said it. It's like the leaf of this. Wait, this is part of the leaf of the Merkle tree that's then proven by the SNARK in the consensus mechanism itself.
Right. So
that's the useful work.
Effectively. We've been reasoning over a number of different design constraints for Proof-of-Succinct-Work, and it's in part because we need it to be really performant. So to actually come up with a performant system for Proof-of-Succinct-Work, it doesn't really make sense, frankly, to actually build a succinct blockchain there. And one of the design approaches we have right now is to construct a small Merkle tree that actually checks the state of multiple subtrees. And these subtrees themselves include, for example, the transactions in them. And so because of that, we actually have a way to then checkpoint state with this. And this checkpointing is what serves as our proof of inclusion. We've been evaluating a few other designs that are effectively recursive to allow us to then extend this even further and also to bake in additional hardness on it. We think that there's a lot of interesting work that's happening right now within like the Plonk and the Plookup space. And it's something that we've also been evaluating specifically for consensus here, to add that into this model.
I think I've never heard that pronounced out loud. Did you just call it the Plookup space?
Yeah, that's how they say it too.
Yeah, I call it Plookup. Is that right? Or?
Is that right?
No,
Plookup?
I mean, it's a new type of gate. And yeah, they do say Plookup as well. So we've covered that you're building a new layer one. I'm curious to hear how. Is this a fork of Bitcoin like Zcash has been doing, or is it everything new from scratch, networking, the whole shebang? So in part, I'm curious to hear how are you actually building this blockchain, but I also want to dig into everything else that's needed to actually make this work, and what are you building there? But let's start on the blockchain side.
Yeah. When we first got started, we really wanted to use something off the shelf that already existed. And we started looking at different blockchain implementations. One of the things that we really had to account for was the fact that this layer one was going to be private by default. And so because of that, many of the architectures immediately were thrown out of the window. But then the second thing was that because ZEXE itself is assuming a UTXO ledger, there's also no compatibility with, smart contract based platforms. And so we had to throw those out. And at the end of the day, there was basically, one or two implementations that we could actually try basing ourselves off of. And the main one that we were looking at was Zcash's implementation. Zcash Foundation has been working on an implementation of Zcash called Zebra. And, that was one that we thought actually had a lot of potential. Unfortunately, just given our timing, it was very early on in Zebra's development, and so because of that, we ended up just going for our own model, and we ended up building this thing from scratch. The repo now is called Snark OS, and it's on GitHub. You can find it under github.com/AleoHQ/Snark OS. And it's written in Rust. There's a lot of modules in it. It includes ZEXE in it, and also Proof-of-Succinct-Work. And it's not battle tested yet. We've been running, and we just started up testnet 1. And as part of that, it's a trusted testnet that's designed to actually battle test the actual system, in conjunction with audits. But secondly, is also just to let people actually try using it and try building on it, deploying things to it, and seeing how it works.
How many engineers do you have on that? Because it's still quite a feat to be able to build that in a year.
Yeah, so there's 4 folks on the team, myself included, who've been working on the implementation of Snark OS for the past year. But we've also gotten some really good extra help from Georgios Konstantopoulos and also Kobe Gherkin, who have been contractors working with us on that initiative. And they've been helping instrument Proof-of-Succinct-Work, as well as with Akis, who's been architecting it from the theory side. Right now we're in an implementation that we think is good enough for getting ourselves to testnet, but we think we still have a really long road ahead to get to actual mainnet. And so, the course of testnet 1 is effectively to start battle testing it, to start stress testing, to start actually poking at it and seeing what breaks, and also just letting users try it.
So let's keep going into, outside of just the blockchain to, make this system work, to build something that's actually usable here. You obviously need a ton of different things. I mean, when we talk to others in the space, they have programming languages or IDEs or various tooling to be able to prove in browsers or whatnot. Like, what other things outside of just the blockchain are you building?
Yeah. Well, first off, I would say the application programming model is something that we've spent a lot of time fleshing out. When we first wrote ZEXE, one of the things that we alluded to was this idea of being able to do private smart contracts. And we gave 3 examples in there. But as you can imagine, that was myself and Petrush and the others hand wiring these circuits in code to actually come up with that model. And it's certainly one that I wouldn't expect, average developers to actually do themselves. it requires a lot of cryptography knowledge. It requires also a lot of careful handholding and just a lot of hope. And it's something that doesn't scale. So, as part of that, we've spent a lot of time thinking about how to design, these types of private programs correctly. And, when we first got started, we started evaluating the different DSLs that are out there today. Everything from Socrates to XJ Snark to Snarky. Recently there's Zinc. And one of the things that we found in evaluating these was that there wasn't a really good kind of developer tooling built with it. And what I mean by that was it wasn't possible to write unit tests or integration tests. And more so, there wasn't really convenient functions to be able to actually get out the type of information you want when you're compiling that circuit. So if you wanted to see at what stage you were at, or what the actual representation of the circuit looked like, there wasn't good serialization tools for us to actually evaluate and make sure that these circuits themselves were standing up to what we expected them to be. And so as we were doing that, what we decided to do was actually to just fork one of these DSLs and build Leo on top of that. And so we ended up choosing Socrates in part because of its maturity. It's been around for a very long time, but also just because of its architecture. We particularly liked the design on how they constructed ASTs here, and more so how the compiler actually reasoned about every step. It was well designed for doing optimizations, and one of the things that with any engineer, they'll have opinions on his syntax. And so we ended up changing the syntax a bit. But other than that, the foundations really did extend off of Socrates. And, since then, I think we've evolved it to a point where it's almost unrecognizable from its original starting point. With Leo, the objective has been to build a programming language that is intuitive and simple to write. We really wanted Leo to look and feel just like a traditional programming language. And the goal here was really for, the normal web developer to be able to write private applications without having to reason about low-level cryptography. Under the hood, Leo is quite complex in that it's abstracting low-level concepts and making it really easy to integrate private applications into higher-level stacks. So the language ended up becoming something that looked far closer to JavaScript than it did to something like assembly. And even then, for something like JavaScript, we found that the design space for it was actually quite well suited for circuits here. The reasoning is that JavaScript itself is actually designed in one environment and ran in another. And what I mean is that you write JavaScript with the intention of seeing its output in a console, but in reality, its code actually is running to manipulate a DOM that is being shown on your interface. And from that perspective, the coder is actually thinking about two different models when they're writing one program. And we found that was quite analogous to the model that we have here with circuits, where users are actually writing circuits to be generated and output and run within a proof system. But in reality, when they're interacting with it to write tests and also to even just debug it, they're really looking at a console here. And so because of that, we realized that this type of syntax that JavaScript already came with was one that was actually quite adaptable to the model that we were looking at.
Are you at all worried though? Like Solidity also is really easy, but has a lot of kind of issues because of its ease of use. There's also chance for a lot of kind of misinterpretations. Are you at all worried about that with Leo? Or I guess that, I'm curious if how deeply you learned that lesson from seeing it happen.
I am incredibly worried about this. And
okay.
All I can say is that we think very hard about this before committing to a design, and Leo is still not in a final stage. The whole point on Developer Preview 1 actually is to get the language out there, is to get the technologies we've been working on out there so that we can get feedback. I'm a huge believer in getting open feedback and iterating quickly, in part because you want good ideas to persist and you want bad ideas to die quickly. So for us, the objective has been to get feedback from people, to hear their input, and also to see what works, what doesn't, what sticks and what doesn't. It's far easier to get that now than after you've baked the cake. And we've certainly seen, with a lot of blockchains that it's really hard to change it and it's really hard to go back once you actually have it on mainnet.
You just mentioned Developer Preview 1. What is that?
Developer Preview 1 is the first release that we've made since coming out of stealth. So for Aleo, Developer Preview 1 is meant to be an opportunity for people to, one, see what we've been working on, but then two, to also try this type of experience that we've been thinking about. The goal here is to provide an intuitive experience for writing private applications. And we've been building out a few different pieces of technology. The first is Leo, which I've just talked about. But also, secondly, we've been working on a package manager for Leo. So the idea is that in order for Leo to really kind of take off, in our opinion, we think that it's really important for the right people to be writing circuits, and for those implementations of circuits to actually propagate across an ecosystem. For example, if you're the implementers of OpenSSL, you should be able to write an implementation of that you can then put out there for other people to import into a package when they're writing their applications. It shouldn't be that every user has to go and re-implement, for example, SHA-256 from scratch whenever they want to write a program. And they also shouldn't have to go to GitHub, search for a file that has an implementation of it and copy paste it into their repo in order for that to happen. I think it's a very common notion within traditional programming languages to have package managers, but within the blockchain ecosystem, specifically with Ethereum and Solidity, it's not so common. And because of that, we have 20,000 copies of SafeMath on chain. And I think that in general, it's not a great design, and it's also something that we think should be standardized.
Cool.
The last piece that we've released is a product called Aleo Studio. And the idea here was to jumpstart the development cycle for developers in DP1. The goal of Aleo Studio itself is to be an IDE to make writing zero-knowledge applications easy. And at its core, Aleo Studio itself has Leo baked in so that you don't have to go and install some separate thing. You just have to download the software, open it up, and start writing your code. But the second thing is also that it's integrated with the package manager. So by doing that, it makes it really easy for you to import and also to publish new packages. But it's also really easy for you to then collaborate with others. So one of the features that we're currently fleshing out is this ability to support teams and organizations so that you can actually work cross-device with other people, whether it be friends or colleagues on applications.
So unfortunately, it's about time to wrap up. But as a ending, I suppose, I usually like to ask and talk about what's coming up next. So you're at this point of Developer Preview 1 and your first testnet. Started working on some language, some of the tooling. What's up next? Like, where are you going from here, and what are you looking forward to?
So in terms of the horizon, we're currently preparing for running a trusted setup ceremony for Marlin. Marlin is a universal Snark and updatable Snark that we're using for programs on Aleo, but also for the Proof-of-Succinct-Work circuit as well. And over the coming months, we are going to be building out the infrastructure and tooling to actually run our setup here. So we'll be building out the tooling and infrastructure for it, and keep an eye out on our channels.
Yes, indeed. That's a good plan for everyone. So Howard, thank you so much for coming back on the show.
Thank you for having me on, and really look forward to coming back.
Yeah, thank you very much. And to our listeners, thanks for listening.
Thanks for listening.